Hello and welcome to this lecture on quantum computing, where we are going to talk, at the beginning at least, about Grover's algorithm. Grover's algorithm is an algorithm for search, so let's think about searching. Well, back in the old days we used to get these huge books full of names and numbers, which were called phone books, and if you wanted to know someone's phone number you had to look through it with your hands in this paper book. It was a different world. So anyway, how would you do this? Well, you could use the fact that the names were ordered in a ordered way. They were ordered alphabetically. So if you wanted to know a particular person's phone number, you could open it up, say, in the middle, and see if the name you wanted was before or after that split, and you know which half to look in. Then you could open that half in the middle, and you could see which quarter to look in, and so on and so forth until you found the specific entry you wanted. So if big N is the total number of entries, how many times do you have to split that in order to find the specific entry you want? How many times can you halve it before you get down to 1? Well, obviously that is the log of n base 2. So the complexity of finding a given entry in this ordered list is O of log n. It is a logarithmic complexity, which is pretty nice. However, what about the case where you're not looking up a number using a name, but you need to look up a name using a number? This is not so easy. There is no structure in the number. You can't look at someone's phone number and think, oh, that looks like a Jacob. Well, that looks like someone called Smith, and have some idea of where to look it up. It could be anywhere, and so you can hope that you find it fairly early on if you go through one by one, maybe if it's the aardvark's number and you're happy, or maybe it's Mrs. Zebra's number and you only find it when you get all of the way through. On average, you are going to take n over 2 entries before you find what you're looking for. And so from the worst case of n and this average of n over 2, we can see that the complexity of this unstructured search is On. So there is an exponential complexity difference between the complexity of a structured search and the complexity of an unstructured search. Can quantum computing help us with this? Well, hopefully, but we'll see in a bit. First, let's talk about something other than phone numbers, which is Boolean satisfiability problems. So these are things where you get some condition on bit strings and you want to find the bit string that satisfies this condition. So for example, we could have 2 bits A and B and be given the condition A and not B. And we have to find a bit string that can satisfy this. Well, that's fairly easy because we know that both sides of the AND need to be 1. So we know that A has to be 1, we know that not B has to be 1, which implies that B has to be 0. And we've got our condition. So sometimes with these Boolean satisfiability problems, we can make use of some structure in order to work out what bit string satisfies that. But that's just like the structured search that we just looked at. We are using structure in order to find a quick solution. Sometimes we do not have this sort of structure, and the best thing we can do is just go through all of the bit strings and say, okay, A is 0, B is 0, that doesn't satisfy it, A is 0, B is 1, it doesn't satisfy it, A is 1, B is 0. Well, that does satisfy it. So the complexity of this is on the order of the total number of bit strings, which for n bits is 2 to the n. And that is horrible, just like that bracket I tried to draw, which was made straight by the Bluetooth. So yeah, is there also some way that we could speed this up? It's basically we're using search in the same way as for the phone book. If there's some way to speed up search, we could speed this up as well. So let's give it a go. What we're going to do is consider a case where we have n bit strings which we encode in qubits, and there is some state that we're looking for. So we have our winning state, and this is just some bit string. It could be an entry in a phone book expressed in binary. It could be some solution to a Boolean satisfiability problem. Whatever it is, it's just some bit string. So that is one important state. Another important state is going to be the state that we are going to begin with. And we want to begin with a state which is not orthogonal to the winning state. But we don't know what the winning state is. So the best we can do is just take a superposition over all possible bit strings, because we know it's in there somewhere. So we know that that is not going to be orthogonal. So if we take n equals 2 to the n to be the total number of bit strings, then we normalize with a 1 over root n. We take a superposition over all the bit strings, but this can actually be very easily expressed and prepared in a quantum computer because it's simply the tensor product of the plus state on all qubits. Now, one other state that we are going to find useful is the state S prime, and that is simply defined as the superposition of all bit strings not including the winning state. So this is not going to be something that we can easily prepare because we would need to know the winning state for that, but it's something that we are going to use in our analysis, and specifically we're going to use the fact that by construction the winning state is orthogonal from this S prime. Okay, so these are the states that are useful to us. There's the state we want, there's the superposition of everything, and there's the superposition of everything except for the state we want. Now we have our important states sorted out, we can define our important operations. One of these is going to be called UF and not weird V as the Bluetooth wants me to have. And UF is a phase oracle which finds the state W. So it assigns a phase of -1 to the W state, and it assigns a phase of +1 to everything else. So for all of the bit strings that are not W. Now there I just put I was going to put not in the set W, which is pertinent for more general cases where there might be more than one solution. But in this case we're just thinking about one solution, so I'll put not equal to W. And so that's the outer products of all of the other states. We also want the phase oracle US. Now this is a phase oracle which acts in the X basis instead of the Z basis. So far we've been thinking of phase oracles as being in the Z basis. They look at bit strings expressed in the Z basis states 0 and 1, and for some certain bit strings they assign a phase of -1, for other bit strings they assign a phase of +1. But we can equally define phase oracles in the X basis, where we have the bit strings represented using the plus and minus states. And similarly, we can assign phases of +1s to some bit strings expressed in the X basis, and -1 to other bit strings expressed in the X basis. So it's also perfectly reasonable to do that. And this is going to be the phase oracle which assigns the phase of minus to the state which is, well, basically our starting state. I was going to write the tensor product of pluses on all qubits, but that is a little bit redundant once we've already given this a name of S. And it is going to assign the phase of +1 to all of the other states, so the sum over everything that isn't S. And we can just use the fact that the sum over all of the x basis states, as with the sum over any of the normal basis, can be very easily written as the identity, and then we just minus the S state off that. So this identity minus the S state is just a nice way of lazily writing down the sum over all of the x basis states that are not S. So it assigns minus to the S state and plus to everything else. Although, actually, it will suit us to have these the other way around. So we like to think of phase oracles as singling out the particular thing with a phase of -1 and giving everything else the phase of +1. But in this case, it's actually going to be better if it singles out the special thing with a phase of plus and singles out, or just assigns everything else a phase of minus. So actually we're going to have it this way round. Of course that differs only by a global phase from the other convention, but you know, it is different. So we can have this more succinctly written as the outer product of S with itself times 2 minus the identity. But in terms of how to implement it, it is a phase oracle. So these are the two things that we are defining. And the important thing is that UF negates the phase of the W state, and US negates the phase of everything but the S state. So that is basically the only properties of these that we need. Now we're going to use the fact that the W state and the S prime state are orthogonal to use them as a basis to write down our initial state S. So our initial state can be written as a superposition of the S state with some amplitude and the W state with some other amplitude. And I should give myself a bit of space to write that amplitude. So we can write these amplitudes as cos of theta naught for some angle theta naught and sine of theta naught for the same angle theta naught. We're not going to make anything too complex here by using complex numbers. What are these angles theta naught? Well, the single angle theta naught. Well, what is S prime? It's the superposition of everything that isn't W. What is W? It is W. And what is S? It's a superposition of everything. So we have everything on the left-hand side of this equation that we need on the right-hand side. We just need to do the right things with the coefficients to make it work. Now S prime is normalized by a 1 over root of n minus 1, but S is normalized by a 1 over root of n. So one little fudge that we need to do is have a square root of n minus 1 to cancel out the normalization of S prime, and a square root of n to put in the right normalization. And that basically gives us the correct superposition of everything that isn't W. And then for the term that is W, we just need a 1 over root n. And everything is correct. And we can see from inspection that sine theta must therefore be equal to 1 over root n. And using the small angle approximation, assuming n is large, we can see that theta is approximately equal to 1 over root n. Now we can start drawing some diagrams. This is the nice thing about Grover's algorithm. It can be understood pretty much in terms of just one graph. So let's draw that graph. And for that I will need the ability to draw some straight lines. So we needed an axis. We are here in this equation writing down S as a superposition of two states, orthogonal states, S prime and W. So let's put the W state up on this axis and S prime on this axis, and our S state begins close to the S prime axis, deviating from it by this angle theta naught. Now what happens if we then were to apply UF? So what UF does is it assigns a phase of -1 to the W component and does nothing to the rest. So by assigning a phase of -1 on the W component, it will change to a state which is now below this axis because it has this negative phase, and so it will be at an angle theta naught below the axis. Okay, so now what happens if we follow up this UF with the US? So what does US do? It does not assign any phase to S, but it assigns a phase of -1 to everything else. So if we look along an axis which is made up of our original S state, which is this one here, and we look at the axis orthogonal to that, we don't really need to come up with a name for it, but basically it flips around this. So it will flip that green one above the blue line. So let's give this a new blue line and go back to having a big thing. So it's going to be equally above the original blue line as the green line is below it. So given that there is 2 theta down here, it's going to be 2 theta up here. So the angle here is 2 times theta naught. So why is this important? Well, we see that by doing UF followed by US, we have taken our original state S and we have turned it into a state which has, oh, I didn't mean to do that. We've turned it into a state which is now got a bigger W component. So we started off with an initial state which had a small component of our winning state, the state we actually want. And we have done these 2 operations, both of them phase oracles, one defined in the Z basis on the winning state, one defined in the X basis on the initial state. And we have ended up with a new state which is now got a larger component for the winning state. And in fact, it's now got an angle which we'll call theta 1, which is equal to 3 times theta naught. And in fact, what we find is that if we repeat this process many times, if we do US, UF, T times, then theta T is going to be hidden by the webcam. So if we do US, UF, T times, then our theta T is equal to 2 times T plus 1, and the important point is times the original angle. So the amount of repetitions it's going to take in order to get us where we need to be depends on what our original angle is. That is the step we are taking, and this step is equal to 1 over the square root of n. And so we can see that the number of steps we need to take is on the order of the square root of n. So the t that we need is O of the square root of n. So by repeating this process square root of n times, we will amplify the amplitude of the w state, which is the state we want, and get to the point of having the w state just written for us in binary. And the number of times we need to do that is the square root of n. So it's not n, which is the best we can do classically for an unstructured search. It is instead the square root of n. It is a polynomial improvement. It is a square root improvement. It's not the kind of exponential improvement that we love to see in quantum computing, but it's a complexity theoretic improvement, and it is important. So that is what we use Grover for. So now we've looked at some algorithms, it's time to start thinking about why we're not actually running these algorithms. Why aren't we factoring large numbers? Why aren't we searching through huge databases? Why aren't we getting insights about large molecules that cannot be done using classical computing? What are the limitations of current hardware that prevent us from doing this? What are these limitations that have to be overcome in order for us to be able to do it in the future? And how might we make new applications that can better work alongside these limitations? Well, that's a pretty big area of research at the moment. And there are three key things that are really pertinent in looking at this. One is the number of qubits that we have access to. One is the connectivity of our devices, and the other is noise. So the number of qubits is kind of an obvious one. If we want to factor a 256-bit number, for example, then we need at least 256 qubits in order to encode that. And we do not have 256 qubits easily available for us to do this on. So we just don't have enough qubits. So why don't we build some more? Well, if you just go around building qubits with no thought about how they're going to work, then you will just get terrible qubits, and that leads to noise. Another thing to consider is the connectivity. So when we're building algorithms, we will just say, well, this qubit can connect to this qubit, and that qubit can connect to that qubit. In terms of connections, I'm talking about things like controlled NOTs and other non-local gates. So there's only a limited set of pairs of qubits on which you can do things like a controlled NOT. So as an example, one of the 5-qubit devices that we at IBM have had online for a long time has this bow tie connectivity graph. So we have 5 qubits, and you can do controlled NOTs between any pairs of qubits that are connected on this. So you can do a controlled NOT between those two, but if you want to do a controlled NOT between those two, that is not directly possible. So this is another question of, given a gate set, is it universal? So given a gate set which only has a limited connectivity, doesn't have the ability to do any pairs of controlled NOTs, but it's just on certain pairs of qubits. Is that still universal? Well, it turns out it is, because you can use the controlled NOTs you have to emulate the behavior of the controlled NOTs you want. You can use fancy circuit identities, you can use swap gates. But it does mean adding in more controlled NOTs in order to close up the gaps in the connectivity. And controlled NOTs are inherently a bit imperfect, so the more of them you add in, the more of those imperfections you have to deal with. So again, there is noise. So this brings us to the big one. The reason why we can't run these kinds of algorithms at the moment is because of noise. Noise means just imperfections. It doesn't mean actual acoustic noise. It means any effects that do things in our circuits we do not want. So when we perform a gate, maybe the gate does not have the exact effect that we want it to have. When we do nothing, we want nothing to happen, but maybe some physical effects will still happen. That qubit is a physical system interacting with its environment. Those interactions are not ideal. Maybe when we try to do a gate, other gates get turned on a little bit as well. Maybe when we do a measurement, that measurement is imperfect, so we don't get exactly the result we want. All kinds of things can go wrong, and that is noise. We need to minimize it as much as possible, and also we need to come up with methods that can reduce its effects even once we have minimized as much as we can, because it will never completely go away. We always need to find ways to reduce its effects in our algorithms so that we can actually run them. And so that leads into the idea of quantum error correction, which we will talk about later. But today we'll just think of simple ways to understand and model noise. So for that, we will need to use the concept of the density matrix, which is another way of representing states. So we're used to having a mathematical object which represents the state of our system, and that mathematical object is a state vector, such as this psi here. So if we want to work out some probabilities, some expectation values, whatever, we just stick this in an equation and it all works. But here's a situation for you in which we cannot use a state vector as the mathematical representation of our system. What if our friend gives us some state psi naught with some probability q naught and psi 1 with some probability q1? What is a mathematical object which represents those two state vectors and a classical probability distribution? Well, for this, let's pick a specific case, which is that we want to find the probability that we get the outcome 0 when we do a computational basis measurement. So this probability is the magnitude of the inner product of the state representing the 0 outcome and the state representing our system squared. So this can be written as that inner product multiplied by its complex conjugate, which can be reimagined as the inner product of our state sandwiched between these zeros. So in the case that we have the probability of 0 over all is equal to the probability that we have been given some state q0 multiplied by the probability that we get 0 given that we've got q0 plus the probability that we've got q1 times the probability that we get 0 given that we've got q1, then this can be written as q0, and I think I'm switching between zeros and noughts as the name for that number in a rather annoying way, so sorry about that. It's just a consequence of being British. I'm going to blame it on that. I don't actually live in Britain anymore, so there's not much in the way of consequences for me to blame everything bad on Britishness, but there you go. Anyway, so there's the equation. You see that we have our classical probabilities in there, and we've got our different states in there. And so we've got everything that we need to represent the state of our system, where we've been given these weird states with these weird probabilities. But we've also got in there the thing we're actually measuring. However, we can rearrange this all a little bit in order to show what the mathematical object will be that is going to represent our state. So we move that all up to give ourselves some space. And basically we're just going to use the linearity of this sandwiching things in between zeros to move the q naughts inside and the sum inside. So basically we're going to pull out this 0 and we're going to pull out the one on the other side, and in the middle we're going to have q naught times the inner product of psi naught with itself plus q1 times the inner product of psi1 with itself. And that's that. So now this is something which takes all of the information about the state that we are using. It takes these state vectors that we've been given, and it takes these probabilities that we've also been given, and it combines them all into one mathematical object. And now if we want to know if we get the outcome 0 when we measure it in the computational basis, we sandwich it with zeros outside. If we want to know the outcome, the probability of getting the outcome 1, we use 1s. If we want to use the probability of some other basis state when we measure in some other basis, we use those, because the thing in the middle is completely agnostic to all of that. So this is what we call a density matrix. So in this case, the density matrix for when we get given the state psi0 with probability q0 and psi1 with probability q1 can be written like this. So here we have a density matrix with an origin story. Sometimes we don't know the origin story. We don't know the probability distributions that have come to make this. And sometimes it doesn't actually matter. I mean, there could be multiple valid origin stories. So one example of a density matrix in this case is, well, let's just take the single qubit. The identity matrix divided by half is a valid density matrix, because it is like being given the state 0 with probability half and the state 1 with probability half. So if our friend were to give us the state 0 with probability half and the state 1 with probability half, then we'd have a density matrix which is described by this. But also, it's perfectly valid to write the identity in the x basis as well. So if our friend were to give us the state plus with probability half, or the state minus with probability half, then again we would have exactly the same density matrix. There would be no way to statistically distinguish between those two things. You'd have to ask your friend. Yes, so obviously one particular case of this is where you don't have the probability distribution, you know exactly what your state is, and in that case it's just an outer product of that particular state. Otherwise it includes some more of this information. So we can think of some conditions that density matrices have to satisfy. One is that they have to be Hermitian. So why is that? Well, you can see that the outer products of states with themselves are Hermitian, and the probabilities are real numbers. So the probabilities are Hermitian, the outer products of states with themselves are Hermitian, so the entire thing made up of those components is also always going to be Hermitian. Also, if you think of a density matrix in its spectral form, then it's going to be some sum over j of some probabilities, let's call them qj, and some eigenstates, let's call them psi j, where for the particular case of the eigenbasis we know that these are going to be orthogonal. And from this we can see that the trace, which is the sum of all of the eigenvectors, the trace is going to have to be equal to 1, because it's just the sum over all of these probabilities. So the trace is the sum over all j of the qj, which is equal to 1. So we have the condition that it's Hermitian, we have the condition that its trace is 1. Also we have the condition that it's positive semi-definite, which means that its eigenvalues must be either real, well, must be real, they must be non-negative, and that is because they have to be probabilities. So we have the condition that the eigenvalues have to be non-negative and they have to be real. We have the condition that it has to be Hermitian. We have the condition that the trace must equal to 1. And anything that satisfies those conditions is a valid density matrix, and so it's a valid expression of a quantum state. Okay, So now we have density matrices, we can start thinking about the effects of noise. Now we all know what happens when we have a unitary that we apply to some state. We end up with the state which is the unitary multiplied by that state. Well, that's at least the ket form. For the bra form, we take the u dagger and apply that to the bra. Now what happens for some rho? Well, if our rho is just an outer product of a state with itself, then we just have to combine these two things. We apply from the left and we apply from the right, and so rho transforms to u rho u dagger, and that is true in all cases as well. So if we have some linear combination of different states according to some probability distribution, again we just apply the u from the left to get the kets and the u dagger from the right to get the bras, and this is how states transform under unitaries when they are expressed as density matrices. So with that we can start to imagine a very simple noise model. So let's say we have a gremlin who is sitting by all of our qubits, and with some probability epsilon x applies an x, with some probability epsilon y applies a y, with some probability epsilon z applies a z. Then what our rho becomes is epsilon x times what we would get if we applied an x, which is x rho x. Well, really x rho x dagger, but of course x dagger is just x in this case. Epsilon y times y rho y dagger plus epsilon z z rho z dagger, and then finally we have the probability 1 minus epsilon x minus epsilon y minus epsilon z times identity rho identity, which we'll just write as that. Now this is a process which cannot be described by a simple unitary. This is something more complex. We refer to it as a super operator. So here we have a super operator acting on rho, which is giving us this new state. So the way noise works is not to be just applying a simple unitary, but to be applying a super operator like this. Now more generally, we aren't just probabilistically applying unitaries in the same way that we are here. We don't have a little gremlin sitting next to things. Instead, we have these more complex interactions of a quantum system with itself and with an environment that need to be captured by super operators with a more general structure. But for our purposes, we can just think of this as probabilistically applied unitaries as being the source of noise. It doesn't completely capture everything, but it goes a long way. In general, we can think of errors as occurring throughout our circuit. For every gate that we perform, we can think of simply as there being some probability that there could be an X, a Y, or a Z error associated with that. That's not the true error model, but it gives us some insight into what's actually happening. And similarly, for a 2-qubit operation like a controlled knot, we can think of there being a probability of an X, Y, or Z associated with each of the qubits involved in that. And then you can probably see how once you've got large circuits with lots of gates, then the amount of those errors is going to build up. The probability that something really drastically wrong is going to happen is going to get very, very large, showing us why large circuits don't really work. Another source of error is measurement error, which is that just when we measure, there's some probability that our result is going to lie to us. Now that is quite easily, well, that could be mitigated with a nice strategy, which we're going to go through now. And this gives us a nice insight into the kind of measurement the kind of error mitigation strategies we can have in the near term to reduce the effect of the errors a bit. But for really identifying where and when things go wrong in a large circuit and sorting that out, we are going to need quantum error correction, which we're going to look at in future. But anyway, let's have this little look at measurement error mitigation. So, measurement error mitigation uses this idea that there is some probability that things go wrong, and we are basically defining a noise model to using in our simulators in this particular chapter of the textbook. And this defines what we call a Pauli error, and you can see it's exactly as I described. There's some probability associated with a particular form of error operation, and then some probability associated with nothing happening. So this error that we're defining here is exactly one of the ones as I described, and then we add this particular kind of error to all of the qubits in the circuit, and we call it a measure error. So this is our noise model, we return it, and we define it for a particular probability p. So here we're going for a probability of 1% when we actually make a specific instance of this. So let us now take a couple of qubits and run a circuit which should give us the outcome 0, 0, and look at what the outcome actually is. Well, we find that most of the time it gives us the outcome 0, 0. It's not much of a surprise, but we also find that we get about 100 samples where we get 0, 1, and around 100 samples where we get 1, 0. So how many samples are there here? Well, we're using 10,000 samples. So if we divide that by 100, then we find that 100 samples is basically 1%. So this is the 1% error that we have defined. This is also the 1% error. And here we're finding that only one sample has come up with the 1, 1, and that's because you need two errors. So one occurs with a probability of 1%, the next one occurs with a probability of 1%, so this is very, very unlikely, and that's why we only see one example there. Now if we make a circuit which should output 0, 1 by putting some x's in, then we find that it outputs 0, 1 most of the time, and around 100 times it outputs 0, 0, around 100 times it outputs 1, 1, and very few times it outputs the exact opposite of what it should do, which is a flip on both bits. And similarly, 1, 0 becomes mostly 1, 0, but with some 1, 1s and some 0, 0s. And 1, 1 becomes mostly 1, 1s, but with some 1, 0s and some 0, 1s. And this time we don't even see an example of there being a 1, 1. Sorry, a 0, 0. Actually, realistic noise will have it more likely for a 1 to flip to a 0 than a 0 to flip to a 1. So really we would expect to see that a 0, 0 would get flipped to 1, 1, far less likely than a 1, 1 would get flipped to 0, 0, but in this case we're just using a nice, easy super operator defined by unitary operations that doesn't have such biases involved. Okay, so what if we were to take that information that we have just deduced and then get a result like this? What can we deduce from this? So what we find is around half the time we get 1, 1, around half the time we get 0, 0, and we get around 100 samples 1, 0, and around 100 samples are 0, 1. So what happened here? Well, since we have already learned to see samples coming up around 100 times as just being the results of errors, we can say, well, probably they're the results of errors. And probably we were supposed to get 0, 0 or 1, 1, 50, 50. So we can deduce that what we were supposed to see is something more like an equal distribution between 0, 0 and 1, 1. So here's a circuit which actually produces this. We do a Hadamard to create the superposition. And we do a control not to make it a superposition of 0, 0 and 1, 1. Then we measure. And we actually run this. And we find that, yes, we get 0, 0 and 1, 1 as our most likely outputs. And we get 0, 1 and 1, 0 around 100 times. So that, what we saw before, is the kind of result we would expect from that. So we've just kind of manually looked at the kind of results we get out from this noisy circuit, understood something about how they worked, and then used that to deduce what the result should have been when we looked at a noisy result. So let's try to do this a bit more systematically. And for that, we're going to rewrite our counts dictionaries as column vectors. So here's a counts dictionary rewritten as a column vector. So I'm just writing a counts dictionary as a column vector with the result for 0, 0 at the top. So 0, 0 had 9,808 in this particular example. 0, 1 had 95. 1, 0 had 96, and 1, 1 had 1. I'm just writing it out as a column vector. I'm not saying it's a quantum state. There's no ket here, it's just I'm writing accounts information as a column vector. So with this, we can write down the column vectors that result from all of the different results for all of the different input bit strings. So this 0, 0, as we've said, has 9808 for its 0, 0, 95 for its 0, 1. So let's write that in the first column. Here's the 9808, but this time normalized. There's the 95 normalized, and so on. The next column is then for the results from 0, 1. So 0, 0 comes out 107 times. So there's our normalized 107. The 0, 1 comes out 9,788 times. So let's write out our normalized 9,788, and so on and so forth. And the next one is the vector describing what happens when we prepare a 1, 0. And the next one is a vector describing what happens when we prepare a 1, 1. So we've looked at preparations of what all of the output states should look like if we know that it should be a 0, 0, if we know that it should be a 1, 1, if we know that it should be a 0, 1, if we know that it should be a 1, 0. We know what the output state should look like, and now we are looking at what it actually looks like given these measurement errors. We are taking that information, compiling those into column vectors, and using those as the vectors of a matrix. And that matrix can then be used to predict what we would get if we had some ideal results. What would the noisy results look like? So here's our example where we expect to see 5,000 samples come out 0, 0, 5,000 samples come out 0, 1. In that circuit that we just performed. That is the ideal result. By multiplying this now by this matrix, we see what we would get as an imperfect result, what we could expect. So this is explicitly telling us that we should see around 100 times each for the two spurious results, and the rest shared between the two correct results. But that's not really what we want, because we actually want the ideal results, and what we typically know from running a noisy quantum computer is what the spurious results are. So we want to do this the other way around. Instead of applying this matrix to turn ideal results into spurious results, we want to apply the inverse of this matrix to turn spurious results into ideal results. Now, not all matrices have inverses, but we can nevertheless come up with an inverse to apply. So this is an inverse of this particular matrix. And if we apply this, then we can take this, apply it to our noisy result, and it gives us something suspiciously clean looking. It gives us really exactly what we should have got. So here we're just basically learning what noisy histograms look like, and using that information to try and clean them up. So here we can see it actually expressed in the form of a histogram. Just have to scroll down a bit. So here's some noisy results in blue. and then we apply this mitigation procedure and we get some mitigated results. Now this is something that if you apply it naively in the way that we've been doing here, if you want to clean up a single qubit by just preparing a 0 and seeing what the noisy version of a 0 and a 0 looks like, and then preparing a 1 and seeing what the noisy version of a 1 looks like, then this is a great way to do it. If you want to do it with 2 qubits, as we've seen here, it's also good. If you want to do it with any small number of qubits, it's quite good. But if you want to do it with your entire n qubit system, then preparing all 2 to the n possible states and looking at what they give you and compiling a gigantic matrix would be so ludicrously horrible that you're not going to do that. You might as well just simulate the quantum computation if you want to go to those lengths. So in that case, there are also generalizations of this which can help you out for more general cases, but we won't talk about those. This is just to give you a bit of an idea how you can clean up a quantum computation in the near term using error mitigation techniques. There are other error mitigation techniques, but we're not going to cover them. This is the one that's covered in the textbook. And this is part of a chapter on, well, what's the chapter called? It's a chapter which looks at these sorts of errors and other benchmarking, and it's called Investigating Quantum Hardware Using Quantum Circuits. Now we're going to go in more detail in future lectures into the repetition code section, but randomized benchmarking and measuring quantum volume are also useful things that you can look into in terms of how to characterize the errors and characterize the capabilities of a device despite having limited connectivity and errors. But that is basically all you need to know into why quantum computers at the moment are a bit imperfect and why we can't actually currently run these textbook algorithms that we've been describing recently. And that's also what motivates current research into more near-term friendly algorithms. But that's all for today. Thanks for listening.